Good morning, everybody. It's a pleasure to introduce Pascale Jablonka, who I know since a long time. Pascale did her PhD in France. Then she moved for a postdoctoral fellowship at the European Saturn Observatory in Garching. And then apparently she didn't even finish the fellowship. She was hired as a staff member in France. And now she's in leave of absence, and she's working in the EPFL, so in Lausanne. And today she will be discussing the Dwarf galaxies using them as test beds for galaxy evolution. Welcome.
Thank you very much. Thank you very much for the invitation, the opportunity to report on a few recent results I've obtained. It's my first time here, and I'm already very much impressed. So yes, I like very much dwarf galaxies because they are very small systems which are extremely sensitive to all the parameters involved in galaxy formation, first of all, if you are interested in numerical simulation as I am. And also because they give an opportunity to compare what is happening during the evolution of galaxies and at their birth in different environments from the Milky Way. They have a very different star formation history from the Milky Way. They have very different masses, etc. So it's a way to try answering open questions and find solutions, hopefully, to the question that we cannot solve only by looking at our closest surrounding. So I will divide my talk in two parts. The first part is results obtained from the analysis of observations, and the second part on recent numerical simulations. It's all brand new results. Feel free to interrupt me before I'm too long, or if you have any questions. So first part is on the reanalysis using non-LTE treatment of spectroscopic, high-resolution spectroscopic data. And it's the first part. This part one is in fact divided in two parts. Part one, it's in two parts, meaning two papers. And the first paper is on Astrofísica already, and it concerns the atmospheric parameters. And what I will present here is also the second paper, which is the analysis of the abundance ratios. So what are the questions which are sustained by our work? So we'd like to understand how the first stages of star formation proceed in galaxies. If there is a universal path which is followed by galaxies independent of their mass, we'd like to know, and it's all related, what is the degree of homogeneity in abundances, in chemical patterns, in all galaxies, and related, what is the initial mass function in galaxies, whether or not it's universal, whether or not it's biased towards high mass at the very beginning. In fact, I won't really tackle the last point, but I will certainly look at the three first points. And so when I am asking those questions, what I have in mind is that we should have extremely accurate, precise analysis of the data to constrain the models. So what are we facing as limitations nowadays? So I'm here only considering high-resolution spectroscopy because we have the most accurate abundances by this technique. And also we have the largest range of abundances of elements. And since I'm interested in the first stages of galaxy formation, I will restrict myself and ourselves to stars which are below -2. So the very metal poor range, or the very metal poor regime, extreme metal poor regime, etc. So if we're interested in looking at comparing dwarfs among themselves and dwarfs in the local groups and in the Milky Way, we are facing two limitations from the dwarf spheroidal point of view. First of all, we are mixing together samples in different galaxies, which have been analyzed in very different ways. And the second limitation is that usually most of the analyses are done in with one approximation, which is the local thermodynamical equilibrium over a large range of metallicity. And in fact, we know that this approximation doesn't work well at low metallicity. So if you were interested to look at how galaxies evolve, so from low metallicity to high metallicity, this is a limitation because you have uncertainties, larger uncertainties at very low metallicities. Also, the position of your stars along the color magnitude diagrams, so the range in temperature and gravity is quite different from one, can be different from one study to the other, and it leads in fact to large dispersion, and this large dispersion is not intrinsic, and so that you have to reproduce with your models is only a consequence of the way you analyze your data and how you derive the chemical abundances. So why do we need non-LTE treatment? Nelly explained it. First I should go explain what is a non-LTE, but what is LTE first? What is LTE? So LTE is just you derive your abundances, chemical abundances, by making the assumption that the population depends only on the gas temperature and its density. So it's a very simple way of deriving the abundances. So you just combine the Saha and the Boltzmann equations to derive your abundances. You calculate the excitation and the ionization. Non-LTE is really a step forward by looking at all the way you can excite or your atoms. And so you take into account the radiations, and you have to determine the radiative collisional population, how you populate and depopulate your levels, different energy levels. And so it requires models of atoms which are sometimes available and sometimes not. So it's this non-LTE approach is the one that we need, but we cannot make progress, or we can make progress until the atom models are available, because it's quite it needs an accurate modeling. So instead of having non-LTE is instead of having a mean description of your atmosphere, you look at the exact physical state of the stellar atmosphere at any point. So why do we need? So here you see the ratio of the energy balance. It's the energy balance between non-LTE and LTE treatment as a function of the optical depth, so the position in your stellar atmosphere, for a model at solar metallicity, and here a very metal poor star. And you see that sometimes the LTE approximation is fulfilled, so you have a ratio 1 at some point in the stellar atmosphere, but not always. And of course, the departure from LTE is larger, much larger, when you go to lower metallicity. So if you want to combine stars in the same diagrams, which are metal poor or solar abundances, you really need to take into account this non-LTE effect. So what did we do? It's the first step of analysis I would like to expand on a little bit later. But for the moment, what we did is we decided to go for the first non-LTE, full non-LTE analysis in a set of dwarf spheroidals in the local group, and of also a set of stars in the halo of the Milky Way. And so we wanted to compare really what is comparable. So we took stars which are at the same position in the in terms of gravity and temperature, and And the quality of the data should be the same as well. So we have 36 stars in the dwarf spheroidals and classical, which means classical means the brightest of the dwarfs, and ultra-faint dwarfs. We focused on metal poor, very metal poor stars, or metal poor and very metal poor, etc., till -4. And we requested that we had a high spectroscopic resolution, so a resolution larger than 25,000. Good photometry to be able to derive the atmospheric parameters from photometry only. So this is samples of stars in Sculptor, Ursa Minor, Fornax, Sextans for the classical dwarfs, and Bootes 1, Ursa Major 2, and Leo 4 for the ultra-faint dwarfs. And then we have, for all these stars, we had access to the spectra themselves, or we had access to the equivalent widths of which were published. And when we had a doubt about one star or one or two elements, we often had to request the original spectra to check what was the to conclude on our doubts. And so we have 23 Milky Way halo stars with which are metal poor, again with good photometry, and again with high resolution. And these are the papers from which our sample originates. So
So Pascal, thank you very much for this very nice talk. Questions?
So very nice. So my question is that what do you suggest for the simulations? I mean, do you suggest that they shouldn't consider the supernova remnant, the supernova feedback, or should they consider a kind of decreased level of this feedback in the simulations? Because you mentioned that due to the feedback, they don't see, they couldn't see such kind of nice central.
It's just the feedback that you, it's just the, I don't know, it's the epsilon, where each time you have an explosion of supernova, it's the amount of energy that will be released in this fraction of energy that you input in your model doesn't change with time. It will. It's just the number of supernovae that will be decreased or not depending on your starvation rate.
Mm-hmm.
And so, but this epsilon, so really this, you take 3% of energy, and very often people take more than this, and it's very clear why. It's really cultural. It's because very often people, there is a strongest interest in those, but people usually come from trying to reproduce Milky Way like galaxies. They are much more massive, and so they are much less sensitive to this feedback.
Mm-hmm.
So you can use a range of values without seeing really the impact on the Milky Way like galaxy. While on Dwarf, we see that very strongly. And this feedback that we have inserted here comes, this value comes exactly from our study on isolated dwarfs, where we could see that it was absolutely impossible to reproduce the properties of dwarfs if you have very strong feedback. While if you have a low feedback, like we have, you can not only reproduce the dwarfs, but also the Neutron.
Okay, thank you. Sorry, I have other question, if I may. So I wonder how the density could play a role in the LTE versus non-LTE comparison that you made at the beginning. So I wonder how much of this effect that you see it comes from the difference in the density in the particle density of different abundances. I mean, of different metallicities of different ingredients, like iron, like I don't know, whatever, nitrogen or whatever. So, are these also included in this in your simulation or theoretical work, or? So, taking into account the equal number density of the particles. Because I know that.
Do you mean particles in the simulation or particles in the atoms, etc.,
Yes, this one.
But the density, I mean, the physical properties of the atmosphere and of the atmosphere is fully taken into account in the density. The density is indeed taken into account.
Okay, thank you.
Thanks for the talk. In the second part of your talk, you are using the ultraviolet background as the proxy to see, I mean, whether or not the stars are able to form. But I wonder, what is the source of this ultraviolet background? Meaning that part of the thing you are studying or analyzing is star formation that happen in this dwarf system, which are many, right? So my question is that, the solution you are testing about the luminosity, the threshold luminosity above which you have a constant star formation rate, in the middle of which you have a decreasing star formation rate, and below something which you have no star forming rate, no star forming. This is also part of the source of the ultraviolet radiation, right? So what is the proxy you are using to test what is going to happen in the dwarf system, which are on this, which are also part of the thing you are.
This is true that there is at the moment it's not exactly consistent that we are not producing ourselves the UV.
Okay, I think we have now to stop because we will have another seminar. And Pascale will be until tomorrow in the Institute, so just contact Giuseppina and then you can ask more questions. I apologize. Thank you for the speaker.